Hello, my name is Joshua Carrillo, and I am presenting on behalf of my team at the University of Texas at El Paso within the Department of Mechanical Engineering. So our project is mainly going to be a precision painting robotic arm. And as you'll see later, it's going to be using trigonometry to reach its desired end effector position. So the team consists of Judith Artiega, Joshua Carrillo, Gal Torres, and Esteban Ruiz. And our objective is to basically, we're going to have a robotic mechanical arm, which is going to be using inverse kinematics to reach its desired end effector position. And it has applications in both industrial and automotive industries. And it's going to be doing this using a control loop control system, a closed loop control system, which dynamically adjusts the positions of the servo motors using inverse kinematics algorithms. So that way the end effector will reach the position, the desired end effector position. And as you can see, we have an assembly of the entire system right here. So as you can see on the left, we have a robotic arm, which is going to be traversing in the Y direction. And we also have a rack and pinion system that's entirely independent, that's going to be moving on the X direction. And I would like to pay close attention just to the paintbrush, which is the end effector right there. And as you can see, this paintbrush is, it's going to be normal to the surface. The calculations involved to do this are going to be discussed later on, but essentially we want at any surface, we want the end effector to be normal to that point in the surface. So our components consist of a high wonder XRM1S, a micro SD card module, an SD card, an Arduino Uno, a 3D printed ABS rack and pinion system, a 3D printed ABS canvas, NEMA 17 stepper motor, a DRV825 stepper motor driver, a stepper motor breakout board, a 12-volt power supply, and some shaft collars. So, yes, as stated before, it's going to be using two independent systems. So it's going to be using a robotic arm, which it's going to be, as you'll see in next slides, it's going to be using a MATLAB algorithm to calculate the tool paths and allow it to basically traverse across any surface using inverse kinematics. And finally, we're going to be using a rack and pinion system, which will move it independently, horizontally. So that way, the inverse kinematics are going to be less complicated, as we're essentially going to be moving on a plane. Yes. Okay. So our main cycle, it really consists of 5 different things. That's essentially what we're going to be doing. 2 of those things are going to be done in MATLAB, while 3 of them are going to be done in Arduino. So the first thing that we're going to be doing is we're going to be extracting the surface mesh. And we do this by reading an STL file. Then from that STL file, we are going to be using curve fitting algorithms. In this case, we're going to be fitting a polynomial surface. And then from there, we're going to be extracting the polynomial coefficients to basically get an equation of the surface. From there, we're going to be generating the tool paths. So the first thing you want to do is get the X, Y, and Z boundaries. So in other words, like the minimum and maximum positions for the X, Y, and Z. We're going to be defining the end effector parameters. So in other words, like the width of the paintbrush and where the center of that paintbrush is. And that's mainly because we want like the center to be aligned with the tool path. Okay? And so we're going to be calculating, so you also need to calculate the start position, and as you can see right there, this is essentially going to be done by taking the minimum in the X direction, and then it's going to be adding the center of the end effector. So that way, yeah, like I said before, the center is going to be aligning directly with the tool path. Okay, and it also, so it's also to account for like the the width of the paintbrush. We're going to be also initializing the some other parameters. So in this case, the parameters needed to calculate the normal vector, the x direction, and the y direction, and also the incremental step parameters for both the x and the y. Okay, and then from there, we're going to be calculating the surface point on the for the z-coordinate, and we do this by plugging in the since the robotic arm is essentially going to just be running on the e and the on the y direction, and it's also, since it's a very simple surface, in other words, it's only going to be changing the z value along the y direction, as you'll see in a couple of slides later. We just need to plug in the y-axis variable to get a z-coordinate. In other words, the height of where the point is at. And then from there, we're going to be calculating the normal vector, and finally, we're gonna be making a decision whether the y-axis boundary has been reached. If not, then it's going to travel in the y. If yes, it's going to see if the x-axis boundary has been reached. If not, it's going to travel in the x direction, and then it's going to switch the y-axis direction and then travel again in the y. And as you'll see in the next slide, it's going to be essentially doing a zigzag pattern, and the toolpath will be completed once it reaches the x-axis boundary. It's going to be doing the whole thing over and over until it reaches the x-axis boundary. So as you can see, this is the surface that we have, and this is the toolpath that MATLAB will create. So in order to read the file from in order to actually have like the inverse kinematics being performed, we need to first get that toolpath from MATLAB and have it ready to be used in the Arduino. So we're going to be including, in order to do this, we need to include the inverse kinematics SD card and stepper motor libraries. We're first going to be initializing the link parameters for the inverse kinematics, in other words, the robotic arm. We're going to be establishing the reference arm angles, and this is just the setup right now. But after this, we're going to be reading the SD card file, and it's going to be reading the current row of a file. It's going to grab the x, y, and x, y, z, I, and j, and also the k vectors, where the x, y, and z are the points, and I, j, k are the normal vectors. And then from those points, it's going to be performing inverse kinematics, and it's in front of you. You see an equation involving the law of cosines, and this is the main equation used to perform the inverse kinematics. So finally, it's going to convert that angle to the servo reading needed to adjust the positions of the servo motor. It's going to move the robot, and then it's going to move the linear motion system along the x direction. It's then going to check if it reached the end of the file, and if not, it's going to go to the next row to read the next points. And if it has, it's going to stop all movement. And as you can see right here, we initially wanted to test a theory out to see if since the values of the servo motor moved from 0 to 1000, we wanted to both assemble it, like the robotic system, in a way that the midpoint will also reach fully extended up. And as you can see, that's how it's done. That's that each servo motor has a movement of 500 bits. And this is some test code involving the inverse kinematics, and as you will see, it's able to move essentially on the same plane while having the end effector normal to the surface. And I would like to for you guys to pay special attention that every single servo motor is being moved so that way it reaches the desired position and orientation of the end effector. And for our final product, this is going to be essentially what it's going to be doing. It's going to be performing the inverse kinematics, and it's also going to be we're going to tie the rack and pinion system so that way it can move linearly as well. So in conclusion, to further enhance the performance and adaptability of the mechanical painting arm, several advancements had to be planned. We had to have increased access control, so expanding the arm's motion capabilities with additional degrees of freedom to enable complex surface painting, allowing it to handle irregular or curved surfaces more effectively. We also need enhanced sensor integration, and this is by incorporating advanced sensors for real-time surface scanning and obstacle detection, ensuring precise adjustments to varied shapes and orientations. Meaning that for our future work, we want to essentially scan any surface using like an iPhone, importing that into MATLAB, and then generate the curve fitting equation, and then do the rest from there. That's what that last point means. And here are our references.